no.
Huh?
Your board is still no
I
signal.
also need to get like milk.
I'm sorry. I'm sorry.
Thank you. That actually.
Come on.
No, I did it wrong. I had to no, bro, you're fine. My signal.
I had another one that I looked kind of popped in first block. It's a lot. No, it was a different stick. It's a lava lamp, and you squeeze the bottom, and the little beads like float. So it has water inside it, like water for that's a lot of.
As many as I can.
So I was like, Friday.
I check as many as
I already
I
had the
can.
conversation with you guys about the word poem we read today.
Yes,
The one with the
we.
blue.
It's like
He
it
asked you
happens.
guys how long, like, the class wasn't responding to him, right? And he went, how long would the speaker look at? They just got really quiet.
Yeah, no, we had.
How long would the speaker really
Chuck,
look? And, like, everybody in the class just went, 200 years?
No, our class really has like 8 or something people in it. So we're here in Welch.
Okay,
No, it was just straight to Mr.
so
President.
now that we got that covered, so let's talk about,
That's great.
they're all kind of the same version of this. So like if you look at 53, well excuse me, 55. I meant to write 53, I wrote 55, but it's the same idea.
She did.
So on 55, there's a couple of things that make this easy. Number one, it's a 1 liter solution. So you have calcium oxalate, calculate the solubility product constant at this salt at 25%. So here's what you want to look at.
Writing your equation.
What's the first thing you're going to do, Christmas?
Writing your equation.
If you don't have the equation, you are dead in the water. Okay? You cannot do anything. If you do not understand what the equation is going to be, or what the reaction is, you cannot do anything.
I was ragdolled.
Okay? So, if you look on this one, you've got calcium oxalate, which is
Go for it, though.
CaC2O4. Okay? Now, oxalate is just one big polyatomic ion. So when this ionizes, what do you get out of it? Calcium ions and oxalate ions. Now, again, listen to me. And you keep this in mind when you do the lab today. The story of KSP is not the precipitate. The story is the ions up above. Okay? That's the story. So it can only hold a certain number of ions until it becomes saturated. And that's what they're saying. So you take a liter, which is pretty big, and what they're saying is if you just add 0.061 grams of this stuff, if you add any more of this, then it's beyond saturation, and then it's going to form a precipitate. So this is a very small amount. This is like 5 or 6 grains of this stuff, okay, which means that this is going to not hold very much. So if they're asking you to calculate the KSP, so you need 2 things. You need the concentration of the calcium ions, and you need the concentration of your oxalate ions. Now, do you need to square, cube, do anything wonky with those? No, because it's just 1-to-1 ratio. There's no coefficients out in front. Boom, there you go. So you're going to take that 0.0061 grams, convert that into moles. It's in 1 liter. That made the math easy. Okay? So here's what's going to be important. These are going to be in the same ratio of 1-to-1. So if you know what the concentration of the calcium oxalate is, then you know the concentration of the calcium, then you know the concentration of the oxalate ions. You don't have to multiply by 2 or divide by 2 or anything wonky like that, because it just ionizes in a 1-to-1 ratio. Now, when you get to 57, okay? So I heard some like, oh, let's talk about that. Responses. So when you get to 57, Okay? Calculating the lower solubility of silver bromide in pure water. So here's the story. This stuff is going to ionize in this. Again, start with the reaction. So you need to know if anything's going to be squared, cubed, anything like that, which in this case is just a 1-to-1 ratio. So on the first one, you're just going to start off just like this was a Ka problem. You'd go 0, 0, plus x, x, and x. So your KSP is going to equal your silver ion concentration times your bromide ion concentration, which is just going to be x times x, which is because x times x is just going to get you what? X squared. Okay? So your KSP is going to equal x squared. Now, understand when you find that x is actually going to get you three things. It's going to get you the silver ion concentration, it's going to get you the bromide ion concentration, and it's also going to tell you how much silver bromide had to be there to separate into the silver and the bromide. So X actually represents three things. The amount of silver bromide that was there that ionized, the silver ion concentration, and the bromide ion concentration. Cool with that one? No worries. Now, when you get to part B, here's what's different. Now you got a 3 molar solution of silver nitrate. So again, you start with the idea that AgBr is turning into silver ions and bromide ions. So this is like a buffered solution. It's a similar type thought process. So on this one, you're told that because of the fact that it is 3.0 times 10 to the minus second molar solution of silver nitrate, now you know what your silver ion concentration is, okay? Now you know that number. Your bromide ion is still going to start at 0. It's the same process. Oh, I'm going to go plus x. This becomes x. Adding this doesn't make any difference. It's like a Ka problem. So then you know this is, was it 3.0 times 10 to the minus second? Okay? Now, that together, multiplied, still has to equal the same KSP problem. But it's like a buffered solution. So since you've overloaded this thing with silver ions, that means it's going to take fewer bromide ions to get the same amount of value of KSP. Okay? Makes sense. And then the only thing difference when you get to C is that now you're told that it's a 0.1 molar solution of sodium bromide. So now the only difference between B and C is on C you're given the bromide ion concentration. The silver ion concentration starts at 0. Okay? Got that? Now, here's what you, and don't do this. What you cannot do, like on, just because the math is easy, when you look at C and it says it's a 0.1 molar solution of silver bromide, what you cannot do to get the silver ion concentration is that you cannot take that and just divide it by 2 and go, oh, that's 0.05. The only time you could do that is if you said, hey, we're trying to find the KSP. At equilibrium, this is the solution, this is the concentration of my bromide ions. Find the concentration of the silver ions and then calculate the KSP. So here it's a subtle difference. If you're asked to find the KSP, you would take this concentration, divide it by 2. That would be, or if in this case it would just be the same, it would be 0.1 and 0.1 because of the fact that it's a 1-to-1 ratio. But if there was like a 2 or a 3, you divide by 2, multiply by 3. But in this situation, the bigger idea is that you know what the KSP value is. So mathematically, these numbers multiplied together have to equal the KSP. So that's how these can be different. Are you trying to find the KSP, or do you know what the KSP is, and then you find the concentration of the ions? Okay, When you get to question 63, and this is going to be relevant to what you're going to do today. So, ironically, when you really need to know your strong acids is actually when you deal with KSP problems. So here's the story. So what I'm going to do, something simple, and this is what you guys are going to do in the lab today. So I'm going to take some magnesium nitrate, boom, boom, couple of drops. Hydroxide, couple of drops of sodium hydroxide, drip, drip, precipitate, precipitate. Okay? So, what happened just now is that inside this test tube, I added magnesium ions and I added hydroxide ions and I formed magnesium hydroxide. Okay? That's my precipitate. Okay? That's your precipitate. So, I got the very, very, very clumpy white stuff here. So there's my precipitate. But again, the precipitate is not the story. The story is the magnesium ions and the hydroxide ion concentration, Mg2 plus times OH minus squared equals some KSP. So Mother Nature is going to do whatever Mother Nature has to do in that solution up above to keep that in equilibrium. But now I'm going to change up the situation. Now I'm going to begin to add some hydrochloric acid. Okay? So as I add hydrochloric acid, 1G, what happened to the amount of precipitate?
No, there's less.
There's less. Okay? So I add a couple more drops. Pretty much. One more, just for good measure. Though the solution went clear. So here's my question. How did adding hydrochloric acid make that precipitate dissolve?
With the OH, it formed water. The H
So,
plus from
that's
the hydrochloric.
true. So how did that make it dissolve? You're right. You are spot on, Kevin.
Broke up the magnesium hydroxide.
What'd you say, Chuck?
Broke up the magnesium hydroxide.
Why?
Because what is it? What acid is it?
Hydrochloric.
Does it matter? No.
Chloride doesn't matter.
Because hydrochloric acid's a strong.
The CO doesn't matter. CO is not part of the story. What does Mother Nature want to be in?
Equilibrium.
Mother Nature wants to be in equilibrium, right? So let's start with what Kevin said first. So up above, there were some hydroxide ions floating around. And I added a whole bunch of hydronium ions to that. Okay? Now, when you mix hydronium ions and hydronium ions, conveniently we get water. Not hydrogen peroxide, we get water, which is cool, which is the most stable form. Okay? If hydrogen peroxide was the most stable form, all of our solutions and waters would be hydrogen peroxide and not water. Okay? Conveniently, water is the most stable form. So when I when I do this, here's the whole key, and you remember this, what's going to happen in the lab today. What's going to up above, what's going to happen to the concentration of the hydroxide ions? It's going to decrease, right? Because of the fact that the hydronium ions are hooking up with the hydroxide. So I'm going to drop, like a rock, the concentration of hydroxide ions. So Mother Nature is flipped out at this point. Okay? So Mother Nature is going, this is bad. Okay? I'm losing hydroxide ions, but I want to still be in equilibrium. So basically what Mother Nature does, Mother Nature views the precipitate as a bank. Okay? So it's just like, ooh, I'm losing money. I'm losing hydroxide ions. But I've got to maintain a working cash flow, if you make the analogy of a business. So Mother Nature goes to the bank and says, hey, yo, I need some more hydroxide ions. And they go, we got you, okay? We got you. So what's going to happen is the magnesium hydroxide, that precipitate, is going to go, whoa, we are going to change from being a precipitate of magnesium hydroxide into ions of magnesium hydroxide. So if I add enough of it, this is why when I added those first couple of drops, there was still some precipitate in there, because that means that solution up above was still saturated. But as I added more and more to it, it eventually said, whoa, this is not good. So eventually, basically what happened is that the bank ran out of money. It did not have any more magnesium and hydroxide ions to add to the solution, because like you had $1,000 in your savings account, you blew through that, and it's like, okay, we're done now, okay? Because you don't have anything else to add. There's no other sources to it. So when you look at this list on 63, so let's say you're going to start with that zinc carbonate, okay? And again, the story is not the precipitate. What's the story? The solution up above. So you're going to have chunky or clumpy, whatever you want to call it, zinc carbonate. That isn't the story. What's the story? The zinc ion concentration up above and the carbonate ion up above. Now, what are you going to add to it when you read question 63? What are you adding?
Acid.
Strong acid, weak acid. Strong monoprotic acid, which is the code for what are you going to dump in there?
HCl.
You're going to dump a bunch of hydronium ions. That's going to be the key. So here's what you want to look at. Are the hydronium ions going to bond with the zinc? Ooh, got a big finger wave. Why not? What is this? Why this Christmas? They're both positive, right? They can care less about each other. It's like, go away. You're positive. I'm positive. It's annoying. Okay, both two upbeat people. Go get away from them. Okay, so they want some negativity. So here's the question: is the carbonate ion the conjugate base off of a weak acid or a strong acid?
Weak.
It's a weak acid. So that carbonate ion, when you add those hydronium ions to it, it wants to get what?
Clumpy.
It wants to get clumpy.
Clumpy.
Okay? It wants to get clumpy. Let's get clumpy. Now, when that happens, what's going to happen to the concentration of free carbonate ions in that solution? Oh, it's going to go down. So, what's the only source of the replacements for the carbonate ions? The precipitate. So what's going to happen?
It's going to go away. Bye-bye.
Well, it's just going to change forms.
Oh.
Okay, it's still there,
But it's not like...
but it's going to go from clumpy zinc carbonate ion into ions of zinc carbonate.
And then it goes back...
It's still there. Okay, don't think, oh, the carbonate just disappears. It goes away. No, okay? It's still there. It just goes from being zinc carbonate as a precipitate into zinc ions and carbonate ions. Okay? Does that make sense? Kevin?
So then if we added like a couple drops NaOH in there, would it reform?
Yes.
All right.
Now, when you look at the next one, you've got like BII3, okay? Right? BII3, that's the third one.
We didn't have to do 64, did we? We just,
No, you're talking about 63, the other...
63C.
There's
okay. Sorry, I thought you were talking about the next question. I got
Okay. So here's the question.
Bill.
Is iodide the conjugate base off of a strong acid or the conjugate base off of a weak acid? Strong acid.
No clumps.
No clump.
Ooh, so if I put hydronium ions in there, is it gonna get clumpy, and no pun intended, and make high?
No.
No, it's just gonna say no to getting high. Why?
You don't do drugs.
Yeah. Okay, the iodide is cool. It's like, I don't need you. Get away from me. Okay? Not today, Satan. It's not gonna form it. But here's the difference.
Get away.
What about the carbonate ion?
Can't make more sense.
It's going to get, because it's the conjugate base off of a,
Weak acid.
but the iodide is the conjugate base off of a,
Strong
so
acid.
it's not going to get,
Clump.
so it won't become more
They
solid.
can't say no to drugs.
They can't say no to
Because they're
drugs.
weak.
Yeah,
The strong acids, they stay strong. They stay strong against peer pressure.
there you go. If you like that analogy, just say no to getting high. How about that?
I like
Say no to
say no to getting high.
Especially Colorado.
Talk about
I can't use that analogy.
The solution.
Okay.
That's the AP Chem shirt. Alcohol is a solution, that's the one.
Just say no to getting high.
Just say no.
I think we need to
Getting clumpy.
Or clumpy, I could go with that.
Time to get clumpy.
Uh,
Now everybody, it's time to get clumpy.
anyway.
It's clumpy.
What you should see on the green sheet is that, and because I want to make sure that you all can do this. So on question number 2, when you calculate that QSP, and again, you use the molarities after they are mixed. So if you're going to do number 2, what's the first thing that you have to have?
Equation.
The equation. So you're going to make lead hydroxide. So you're going to have PbOH2 forming and 2 hydroxides, right? Okay. You need the concentrations after they are mixed. Okay? So if all goes well, your QSP calculation is going to be around 1 times 10 to the negative third. Okay? Now, here's what I want you to see. The KSP of lead hydroxide is a really, really, really small number. That's 1.2 times 10 to the negative 15. So what that means is that if you multiply in equilibrium the lead ion concentration times the hydroxide ion concentration squared, Mother Nature wants you to get 1.2 times 10 to the negative 15. That's what Mother Nature wants, okay? It's an incredibly small number, so that means your lead ions and your hydroxide ion concentrations are going to be really, 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 really small, okay? So you come along and you say, hey, after I mix these, I have a QSP of 1 times 10 to the negative third. QSP is like a snapshot. It tells you, hey, this is what we have right after we've mixed these solutions together. So is this number bigger or smaller than your KSP? Bigger. Mother Nature goes, this is bad. This is very bad. Like Mother Nature was flipped out. So she can't just chuck the ions over the side of the beakers like, you get out, okay? Which would be cool to see little ions flowing out of the beaker. So what's the only way Mother Nature can get rid of the ions?
Tell them to sit down.
Tell them to sit down and they form a
Precipitate.
precipitate. So that when you reach back to that equilibrium, it gets back to that point. Okay? Got that idea? Now, there's one concept I want you to see. So, I'm going to do this. I'm going to take some sodium hydroxide, same thing, add a little bit of magnesium nitrate, okay, and it got clumpy. So part of this is terminology, and you need this for the lab. So I've got this precipitate down here. So centrifuges. Have you all worked with centrifuges before?
Yes.
Let's go with no, you haven't. Okay, so when you work with centrifuges, number one, make sure that you work with the short little test tubes. You also want to make sure that they're balanced. You cannot run a centrifuge on one test tube. At a minimum, you have to have two and have them on opposite sides. So, here I have one. Let me just move this back here. You hold on to these.
Yeah,
Thank you. Got them?
yes.
Okay. So, for those of you in the studio audience, okay, so these are numbered 1, 2, 3, 4, 5, 6. So when you do these, and sit up, thank you, 1G. So you're going to put them on opposite sides. You want to make sure that they kind of have the same amount of volume in each. Now, if you only have one test tube that you need to centrifuge, because it spins really, really fast and it creates a false gravitational field. If you only have one that you need to run at a time and you don't have like a partner, you don't have two, what you can do is take another one, it's called a water blank, and you fill another one up to that same volume and you just use water. So that way you have what you want to precipitate on one side and you've got a water blank on the other. So you can run 2, you can run 4, but you can't really run like odd numbers because you want these to be balanced out. So when you get this up and going, Kevin, you might have to like give that a quick spin. Hold on. Okay. So to run it, you just close it. And then some of these are old, so these have gotten a little bit out of balance. So you might have to like put your hand on it, kind of like a seance kind of thing. Oh. Actually, this one is bad. And there's still a little bit. Okay? So just get it up to speed where it runs pretty fast. And then just turn that knob back. Just let it run up to speed for like about 30 seconds. That'll be enough. And then you want to let it slow down. So these spin at about 4,000 revolutions per minute, which is really, really fast. So if you're inside of there, you would feel a force of gravity about 1,800 times greater than you do right now. Okay? Bones break at about 20 Gs. These are at 800 Gs. So if someone shrinks you down to the size of Ant-Man and says, hey, let's go in the centrifuge, don't go. So once it slows down, so what happened, so this is the one that had that precipitate in it. Notice that all of that precipitate got settled down there at the bottom and the solution is up above. So that's one of the things you're going to do in the lab, is that you're going to separate out a solid from a liquid. So you run it, then take it out very quickly, because if you move it around too much, then that precipitate is just going to dissolve back into the solution and there's no point in what you did. Okay, so with that said, and this is what I want to point out. So now, to this, I'm going to add, can you, yes, it's okay. You're fine. Okay, now, this is such a non-precise thing, okay, but you're going to get the point.
Can't
So-
believe you did that.
Back off me, okay? So, I'm going to add just a little bit of water to
A wine
this.
glass?
There's water.
This was such a strange
So,
thing to do
It turns
just
into
now.
wine on
You took it, you just got the white powder all over and then you just poured some
We're kind of
water.
water in the wine.
Didn't even measure it from a wine glass that has been sitting here for like 2 weeks.
You dumped a bunch of white powder on the floor.
True story. Okay, now, here's the thing. I added some water, but the precipitate is still there. So what happened when I added the water when I initially added that water, what would have happened to the concentration of the ions in the water above, in the solution above that precipitate? When I initially added the water?
Decrease.
Well, it decreased because I added some water to it. Now, but notice that you still have a precipitate. So what that means is that as long as you see any kind of precipitate, as long as you add water and you still see a precipitate, that solution up above, there's a couple of ways you can say it. You can say that it's still saturated. You could say that it's still at equilibrium, okay? Now, am I decreasing the concentrations by adding that water? Absolutely. But there's still a bank of precipitate. So if you add water and there's still some noticeable precipitate after you add the water, the concentrations have not changed. Now, did some of the precipitate dissolve? Absolutely. Okay? But it still maintains that same KSP value. Okay? Does that make sense? All right. Any other questions on? So let me give you another hint. So the QSP on number 2 should would make a horrible GPA times 10 to the negative third. And your QSP on number 6 would make a better GPA, but still not so good, times 10 to the negative fourth. Okay?
Yeah.
What about what?
All of us are,
One on the book side.
all of us are,
I think I got it. Oh, actually, I checked it.
Okay.
I don't know what.
So let's talk about 61 because you're going to have questions like this on the lab.
Rangy?
What do you start with on 61?
Equation.
What's the reaction?
Magnesium hydroxide.
Manganese or magnesium?
Manganese.
MnOH2 is turning into what?
Manganese ion.
And 2 hydroxides. True?
Yes.
Good. Now, here's what you've got. So your KSP is 1.6 times 10 to the negative 13. Okay, if you go to the back of the book, there's your KSP value, 1.6 times 10 to the negative 13. So what that means is that when I multiply my magnesium ion concentration times my hydroxide ion concentration squared, I want to get that number. Cool with this. Now, so on 61, on that first one, you're told that the pH is going to be at 7. So if you have a pH of equal to 7, what does that mean? What can you figure out relative to this problem? Oh, now you know your hydroxide ion concentration, which is 1 times 10 to the negative 7th. But that's going to get squared. So your manganese ion is your unknown. And your KSP is 1.6 times 10 to the negative 13. So when you find X, because it's a 1-to-1 ratio with the manganese hydroxide, once you find X, that's 2 things. It's the concentration of the hydroxide ions. It's also the concentration of your MnOH2. So once you get that number, which is going to be your answer, that manganese ion concentration should be something close to your age. It's a big number, okay, for a molarity. That's a big number. So then, and again, it's nice because you're told the fact that it's just 1 liter. So then you're just going to take that 16 moles, which is what you should get as your answer, and then convert that into grams. What? How
It
big?
was 16 times 10 to the 10th, whatever.
Yeah, that's a big, yeah.
You said big number, and I was like, oh yeah, that's got right.
Not that big.
I'm not 16, you know. So
Oh, big
number, good.
Pretty sure you have one.
Okay, I got 6. Just 6.
Only one up. Oh, no, no, no. Never mind.
You good, Sean?
I thought blood was spelled
I
with
think
two
I was reading it wrong, and then I just got
It is.
plain
Wait,
old
for
6.
Just 6. I mean, if you put one in front of it,
Look.
it's like,
Yeah.
The
No, I get the thing, I just don't know what I did wrong.
Blood.
I think I did the wrong thing.
Look, you're dividing by 1, your value of x
Yo,
has
my
to
answer is
be,
good.
just involve a 1 and a 6.
Well, I know, and that's why I knew that 6 wasn't right. I just don't know how I got it. It's okay.
That's the answer.
Okay,
Yeah, you have something wrong.
now, when you get to B,
Oh, that's.
here's
that's
the trend
that's
that I
the-
want you to see.
I forgot to switch it back to the.
When you look at 61B, here's what's different. You're told now that the pH is 9.5. So what's happened to your hydroxide ion concentration? It's gone way up, and it's getting squared. So what's going to happen to your manganese ion concentration? It's going to go way down because you have a higher concentration of your hydroxides. So your molar solubility is going to go way down.
I saw you both looking over hungrily.
Wait, did you get 14, 20?
Yeah, those were the answers. Yeah.
What did you do with it?
Is that, are we good?
I'm good. They're not good, but I'm good.
Oh, that was, yeah, you were right. You had 4 written down for some reason.
So here's what I want when you hand this in, Mr. Grinchy.
Happy birthday.
Thank you. Merry Christmas.
I'm
So,
weird.
here's how I want this handed in. I want the green sheet on top with where it says your name on it. That's gonna be page 1. When I look at it, this is what I see. The sheet that has your name on it. Then I want the book problem stapled to the back of that. Green sheet, your name, book problems after that. Okay. Kevin, stop, you don't have a camera.
No worries.